Wonderful, guys. We are live, and it took a few minutes before we had to make things a little bit organized. So, this is Terry from Amsterdam, and that is Tanishta from Toronto,
Toronto.
and we have Kwamar who is in India. So, we are all spread across the world. And now we are trying to, obviously, we are going to go through a presentation of this wonderful research that you may have seen me repeating several times on LinkedIn, probably to some of you a little bit of an overload of information. But I still insist that that is the overload that we need, which is invention and innovation. So I'll just give you a brief sort of introduction around the invention and innovation. So first of all, obviously, before that, for those who are joining this session for the first time and don't know us, I am Terry. I am CEO and co-founder of a few companies. Deep Kapha, Kurai is a healthcare company. Then Live AI is our training platform in which we're going to be doing all these amazing projects together with you. With me, you have seen Tanishta as well in a few information sessions we did for the worldwide community. Tanishta is actually the co-founder and I'm saying already CEO of the startup which we are now incubating inside Deep Kapha. The core principles around that startup is earth sciences. So we look at two things. We look at let me see. Obviously, I see all you guys are here, so it's great to see that. Hi, Sharif. Hi, Samantha. Great to see you. Hi, Sweta and Khalil. So it's really wonderful to see you guys. And so as continuing, so earth sciences is something which Tanishta is amazingly sort of not only passionate about, but she's been the driving force around this initiative. And what we're going to be talking about actually today is about this whole idea of invention and moving and pushing it to innovation. So let me start with invention. Last year, I got in touch with Tanisha close to 2 years ago. I reached out to her when she had written a wonderful piece of article around geophysics and machine learning, and essentially, hi, Saikat. And so I said, hey, we are doing a startup, and together with G May, who is also a management team member, just like Tanishta, I said, do you want to be part of our research? And that's how it started. And last year, Tanishta came and she said, okay, I want to actually, go deeper into the earth, literally, and understand, how can we sort of understand the facies, which she will explain in greater detail to you guys. And so basically, Tanishta and me started talking, and I was kind of already a little bit sort of like, okay, research is not easy. It's not easy to first come up with an idea, and maybe it's easy to come up with an idea. It is not easy to bring it to fruition. I have seen that in my past 2.5 decades, 25 years of working career, that even when two people sit and want to write a paper together, it takes literally at least 4 to 5 months. And these are two really driven people. Um, so 1 year ago, we started this journey, and out of that journey, PETAI, or Petrophysics AI, was born. And last week, just 2 weeks ago, less than 10 days ago, long story short, we presented our work, including an invention, at the GeoConvention conference in Calgary. It was virtual, obviously. And so that invention actually was a great step. But Tanisha was pushing me all the time. She says, we have to bring, and one, we have to keep improving our models. Second, we need to bring it to innovation, to bring it to enterprises. And how do we start testing and this model? I cannot go into the detail of that because that is still confidential information. We will sort of spare you the details. Hi, Gautam. But The thing is, we are working on some, we're going to be coming with some massive announcements with our partnerships with some universities that actually specifically focus on earth sciences. And one partnership is already underway. We'll have a signature and we'll let you know. And we are also working close to getting our invention into innovative pipelines of customers who really want to work on this and improve and optimize their models, current models. So Tanishta will explain to you in great detail about it. So we have with me Tanishta, and we also have Kwamar. Kwamar is struggling a little bit because he's in India, and I think there are some mic issues. And we'll do our best to have Kwamar as well take up his part and give you this 40 minutes max, 35 to 40 minutes kind of a presentation. So this invention is fascinating. We have invented Earth Adapt Net. It is a deep domain adaptation algorithm. And just to give you a bit of a small perspective around domain adaptation is a subfamily of transfer learning. Transfer learning is you can take ideas, learnings from one domain, and you can put it into another domain, while in domain adaptation, you're actually working within those domains in industry vertical, within that industry vertical, and actually can reapply these with very limited amount of data. So that's a really high level information. Obviously, we go into much, much detail when we do our workshops in live AI, our applied AI essentials. But absolutely super excited to have you guys here. And yes, Shashank, as much as you say I'm an influencer, I think to me, when we work together in Deep Kafa, me, Tanishta, Kwamar, Ayush, May, there are like 30 people right now in our team. We are thankful that we are able to keep our feet on the ground and we are able to focus on the real world problems. If we can influence with our inventions and innovations, then we would consider ourselves on the right side of the AI development. So I hope you refer to our work, with which you are able to learn from us, through which we can learn from you, from your feedback. So I'm very grateful and thankful for this. But my influence is coming because of this wonderful team. Today I was driving inside a car, just to give you a real world example, and I was thinking, actually, I could have done nothing of this on my own. It was impossible. I mean, it's because they put their tremendous amount of efforts, Tanishta, May, and we are coming up with some wonderful, wonderful tools and products and inventions, even software. It is impossible to do it on our own. So, I'm just standing on the shoulders of this wonderful and brilliant and amazingly fine and, the sweetest people that I have the fortune, and I thank God for that. And that's how things work. I mean, in a big company or a small company or a startup in academia, you need to work with great people and great professionals. I keep saying that on LinkedIn, but I will just say that again for one last time. Oh, for today. Tomorrow, I'll say that again. So, having said that, I want to give the floor to Tanishta and Kwamar because those guys are the heroes who made this happen. Thank you so much, and let's get started.
Hi,
And
everyone.
hey, Bjorn from Denmark. Go
Hi,
ahead,
this is
Tanishta.
Tanishta. Thanks, Terry, for the kind words. And PETAI won't have been possible without your support, so I'm very grateful to you. And also grateful to my team members who are Jimei, Kwamer, Ayush, and Rifat. So all of us struggle so hard to make this work. And I think it was around 2 weeks back, we did our first presentation at Geo Convention in Calgary, as Terry mentioned before. And it was really appreciated well over there. So what I'll just quote about what was the idea behind PETAI. I mean, it was, as Terry mentioned, that it's mostly and going deep into the earth. So that's mostly the goal, that going deep inside the earth and looking anything related to earth and energy. But this project that I started working out is because I am a geophysicist and I have a PhD in geophysics from U Calgary. So the obvious project that we I wanted to do was help oil and gas companies, like because there is a lot of scope over there, and these big giants want to do automation in their industry. So that's the reason we started out with this project of doing an automation of seismic interpretation mostly. So let me go about getting started with the presentation and give an idea what we actually did and how this great people working with me actually got this Earth AdaptNet working around. So I think Firmer might be able to join, otherwise I will kind of drive. But Firmer has done a lot of part in training these models, and we are actually writing a paper right now. So let's maybe I'll just share my screen.
Awesome indeed. Kwame did a lot of work together with Ayush. Let's not forget Ayush. So, in a strange way, I mean, Tanishta has a background in IIT from IIT Kharagpur. She did her master's there, and then I just, like I said, mentioned yesterday, Kwame was so inspired with the research that he's moving and he's doing started his PhD at IIT Kharagpur. Ayush is from IIT Kharagpur, so it's almost it seems like this is like a Kharagpur and Deep Kapha collaboration, and we need to talk to the faculty there because a lot of magic is happening. Go ahead, Tanisha. Let me just share your screen. So here you go.
Sure. Okay. Even though we are talking around PETAI, but we will today kind of focus how we came about inventing Earth AdaptNet. So the talk is mostly generating a SOTA algorithm, and this is what we have applied on Seismic Facies. And of course, it's a PETAI initiative. So as I mentioned that this was the first project we looked at because it's mostly oil and gas problem. So here you can actually, so where is the oil? That's the big question oil and gas always want to know. And for these, they are drilling everywhere, trying to find new places to get the oil and gas, stuff like that. So this is a deep sea drilling rig, and there's so many drilling rigs all over the world. So and there's a lot of money involved around around these getting the right location for oil. As you see, like it's just 50 million that goes into mapping the areas. But what do I mean by mapping is like find potential areas where you might have oil. Then all these drilling rigs are so expensive. There's like $100 million, and to get a drilling rig at that over there. But after you do all these problems, then you actually get a very good revenue. That's why this industries keep going on. So what's there beneath this? Like, what is the oil and gas trying to do? Like, what are they looking at? What's their data set? So their data set is basically a seismic section like this. So it looks very pretty. I'd say not really nice, quite ugly. But the what you have to know here is it's actually what you see beneath this oil rig mostly. So it's kind of a time series data that is showing you the different layers of the Earth in the time series. So all these riggles are collected in time series, and that's what we have as image. So, why is this an important challenge? Like, why is it challenging? Because oil and gas do a lot of research around this area, and they get a lot of data. But then the problem is these reflection patterns, as you see here, are quite difficult to understand. Like, and if one person is looking at it, he or she might get lost very quickly in this kind of data set. So, I mean, many of you might not notice it, but this is how geophysicists try to identify it. So this is kind of, if you see, we base it on the amplitude. So these two arrows are indicating that these are parallel sections. These amplitudes are parallel. So it has a different geological setting. It happened in some other, like it has a different rock type. Then the middle figure over here, sorry. So the middle figure over here is also has a reflection pattern which is quite different from the earlier one. because it has self-parallel settings, and this is also related to a different kind of rock type. And the last figure over here, it is also uh, it is also quite different from the other two because it's continuous, but it's also breaking, and sometimes there is no amplitude seen. And this is very difficult to interpret. So imagine a person looking at all these, like a big structure of this day in and day out, is going to get lost in this. So this is where machine learning is very helpful, like to automate this process of finding out the rock types, or as we call, it's called like seismic faces in our geophysical terms. So faces is mostly like different rock types. So let's go there. So there are some a priori properties. So we kind of started looking at, this is an F3 block from Netherlands, and it does have so we did had a raw seismic data. It's at the top, and then there are labels at the bottom. So these are labels that the geophysicists have marked. So we were fortunate enough to get this data set, but it was really not a very big data set. So it had many challenges on going about training this kind of model. So, I mean, if there are some geophysicists out there, they can understand that these are facies classes or different rock types, and these are the name of the different faces. But as you can see, there is a lot of class imbalance happening here. And it was very difficult to get the last three classes. And those classes were actually the important classes that would provide where is the oil answer. So this is a data set that many researchers are also working out in the world, and we also took this data set, which was publicly available, and we tried to approach it in a different way. Also, some priori properties we knew was there is if we do overlapping sections, then it would have give us much more better quality results. What do I mean by overlap is break down these sections. I'll talk about it later on. But breaking down these sections into smaller patches so we generate more data set to train our model. And also, like these are few seismic properties. It's a gray level co-occurrence matrix that depends on the type of cells, the neighboring cells that happens in a grayscale, stuff like that. So this study was previously done, and we knew that there is quite a bit of dissimilarity between these classes. So the model might be able to train on those kind of dissimilarities, basically. So, so why is this difficult? I mean, training a model, getting the right model is difficult anyway. So, and it's very frustrating, as you can see the cartoon over there. That's what happens to many of the people. So I did this Google search, this search from Scholar, I think 2 days ago, and I just put semantic segmentation architecture, and there's like 20, more than 300,000 kind of papers right there that has this that talks about this. Then I did a search on UNIT. So UNIT is one of the famous architecture that is used for semantic segmentation of this semantic segmentation. So even that popped out and gave like 21,000 results. And then I did a seismic semantic segmentation search, and it was like 3,000. Well, it did narrow down, but it was still a lot. So how do you start it? Like you do need to get some idea of how to start it, right? So so that's the reason what you have to do, like what we follow in Deep Kappa is uh, we get we need to have a workflow that we follow, and then we iterate through those like we have the workflow, and then we iterate through few of the steps to get the actual architecture. I mean, definitely we need a background information, but then we also need to come up with a workflow to start out building the model. And then we need a strategy. It's similar to the workflow. So this is how we kind of started following, building up Earth AdaptNet, and then it's Earth AdaptNet, and yeah. So this architecture was actually one of the what I say is properties, or what this architecture did was, as I showed before, there were three classes that were really. I'll just go back. Probably I'll just. So these are the three classes: Windland, Scruff, and Jetstream. So these are the three classes which were never showing up because of their class imbalance property. But what Earth AdaptNet was able to do was pick up these classes and show a very good accuracy around it. So this is quite a big improvement than the existing models that is there. So yeah, that's basically that what it did very well. So how did we go about building the Earth AdaptNet? So this is how my team started working. So as I mentioned, unit is a very like an important architecture for semantic segmentation, and also it has own few challenges for detecting salt in seismic sections. There was a big challenge that happened in 2018, I believe, from a big oil and gas company, and this architecture proved very useful over there. But it's been 2 3 years after, then there's a lot of improvement that happened. So that's the reason our choice was to do an unit fit. But unit started overfitting. It was really it was what we expected of, because unit really trains on very big sections, which we were not providing it. We wanted to do a patch based architecture basically, so we produce more sections, and then also get more computational power. So that way we just didn't wanted to use unit. So what's the next step is we have to select few selection strategies. So how did we start going about selecting those strategies? Is the model was only the input model was this size. So and the data set is highly imbalanced. Sorry, this is a little bit wordy slide because these are actually the steps we followed. So just sharing with you. So and we were not we didn't want to train the entire sections because there were not many sections and it would take too much computational power. Also we started choosing patches that did had some overlapping between them, and one of the very like I would say one of the most important factor is how do you choose a matrix around it. So there can be many metrics like intersection, then mean class accuracy, uh, and there are a few more actually, precision, recall, and stuff like that. So we did had few matrices in hand, and then we thought that we can go about optimizing the mean class accuracy actually. So that's what we stick to, but we did play around with few more matrices as I mentioned, and maybe there's a few results at the end that will show that these are the matrices also we considered. So yeah, choosing a matrix I felt was also one of the important strategies we had to come around. So finally we started doing our first run. So this is an iterative process. So it depends on the model complexity and also stuff like that. So there are few information here because we did started training it on Deep Lab. That's been very famous it's from Google and it's very famous. And then we also started training it with another encoder decoder architecture that was previously tested by few people. So it's with a residual and block. So these are few things we tried to consider. We wanted to train it from scratch. We considered using ResNet 7 or 9. Then we considered some skip connections. Then we tried to see like at each iteration, whatever results was coming back, we tried to see how the field of view is affecting. Changing the number of encoders. These are the few things we actually started experimenting with. Of course, there is a lot of debugging and errors happening here, maybe because of implementing different type of architecture. This is quite a chaotic process because at this stage we need to do few like we come up with few models and we're doing the refinement, so it's quite difficult to get lost in this part of the process. But anyhow, we try to keep a track of it. And yeah, so going forward, we then try to do a model performance evaluation. It's basically we have these results from few models, and then we started comparing each other how well the matrices were performing. Mostly the MCA, but there were also other matrices that came into consideration. Also looking at the sections was very helpful. So, and we, yeah, this is how what we kind of did. Then came the parameter tuning. So once this kind of we had some idea on which models were really performing well, we did discard the other models, and then we started doing the hyperparameter tuning. So this is where we did some learning rate, batch size, and activation function. We tried to change few of those parameters and see which one was giving the best result. So this the entire architecture we did to train on a Google Colab, so it didn't take that much computational space, and it was quite efficiently running there. So here at this point, we also did few parallel runs because of the hyperparameter tuning. So then we try to then once all these were done, so we have two or three models with two or three good hyperparameters that we can use for, and that's how we actually came up with Earth AdaptNet. So, and that's the final model. So as I was mentioned, which is the patch based model. So this is since we didn't have that many data sets, so we did a patch training. So patch model, we take sections of the model which were kind of overlapped. So this is an example where we can see some of those patches that were trained there. Though patch have a few different problems, it might not store its special locations, which we are actually also dealing with right now to improve the model on. But it did prove a lot faster than the section models. So in this, this is what we started working out with, and then we did a data loader where we did other image kind of image augmentation like rotation, translation, uh, some kind of filtering and stuff like that. So yeah, this is how we started getting a little bit more data set out of the limited amount of data we had. But this is quite a common procedure that is actually done. So basically, so then as I mentioned, I think let me just check if Kwame is he is available. He did this kind of training, so I'll just see if Kwame is there. Okay, is Kwame there? Terry, no, he. Terry, you are mute. You are muted.
All right, sorry. So he was just having really horrible trouble with joining from
Mm-hmm.
India. The internet was really bad, so he may not be able to join. Is it something we can
Yeah,
complete?
let's
Maybe
just
just
do
high
high
level,
level.
and
He
then we
might
can wrap it
know a
up.
little bit nitty gritties because he did the training, but I can just
Yeah, just stay on the high level. I think people have more. I'm looking at questions. The questions are also rather very interesting, but high level. So if
okay,
you can just
sure.
give a rundown to talk about, yeah,
Oops,
yeah.
sorry. Oh, okay. Okay, so I mean, this is the architecture that we I finally chose. It's an encoder decoder architecture. Many of you know that it's like so. What is encoder? I'll just iterate through. It's like it takes an input and gives out a feature map, like in the space over here. So it's an input and makes feature map here, kind of downsampling, and then it upsamples and give an output. So we match this output and with the original labels, and that's how it's kind of the architecture works. So for this problem, we started out with there are very many pre-trained models, but we didn't use these because there were AlexNet, ImageNet, and VGG16. So we didn't train on any of this because these were never trained on a seismic data set. So the weights we didn't think were any useful to us. So actually, that's the reason we started using the models from scratch without any pre-trained models. So probably, yeah, okay. So this one is a ResNet 9 architecture. Maybe we can. It's just an architecture. Think this is the one that gave us the best example, best
Mm-hmm.
result. So why did we choose this architecture? This actually we had to go through a few iterations in choosing this one without any pre-trained weights because of our patch size. There were no literature around this, like if you have a patch size of 99 cross 99, what's your best ResNet architecture that you have to use? So this is what we came about going around and choosing this ResNet 9 with few iterations. Um, and then this is basically ResNet 9 with a basic block, and then it has a bottleneck block. So I'll go high level. I mean, this ResNet is a lot of things, but this is a ResNet 9 architecture basically.
Mm-hmm.
So as I mentioned, we started with we were trying to compare our architecture with some like the SOTA architecture that's already there. So DeepLab V3 is one of the architecture that really proved well because it has an across spatial pyramid pooling, so ASPP, which gives you more view in terms of like it's also a encoder decoder architecture, but it gives a more kind of view when you get the final model. So this is where it did prove well in some like it did prove well in few of the images, but it was never tested on a seismic network also. So what we did was also we tried with this architecture and it did give good results, but with the classes that did had good did had good class balance, but not for the smaller classes. It didn't do anything good over there. But we actually this part was interesting, so we tried to also go iterate through these and see how the ASPP was working and if we could include this architecture to our architecture. So 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 this is Earth AdaptNet, and let me just go through. So it's basically, this part is basically kind of the unit. It's a convolution layer. And this is the residual block, which is basically the encoder part, and then the transpose residual, the decoder part of the block. And it's also okay. So, and we took this part of the ASPP that I talked about because it was doing improving the field of view. In many of those literature, we did find out. So we thought that once this architecture was built, we thought we'll also include ASPP to test how this is performing. So yeah, so these were the two final models that we came up with that we tried to compare with DeepLab, and I believe we would have a result. So let me talk about around the results. So as I mentioned, we did like a comparison with DeepLab, but then there was a baseline paper that also came up in 2019, and they did had used this similar data set and also similar patch models. So that's the reason we thought it's a good idea to compare with them and see how this architecture was giving better results. So as you see, it was actually able to pull up these classes which were not found for their architecture. So I'd say we did quite a good job on there because, as I mentioned, these classes were really important to figure out. Then we also compared it with DeepLab. There's a Even though DeepLab kind of did somewhere better, but it still didn't compare with the architecture that we generated. So that's the reason we kind of think that okay, this would be a quite a big leap from what like if we have really a very challenging class imbalance problem, especially for seismic data. So yeah, so that's our results. There's a few sections. I mean these are original and these are the predicted ones. A few of these areas which didn't show up was because of the class imbalance problem, the smaller classes. And our next model that's an improvement of this is basically dealing with this spatial problem. So yeah, stay tuned. We are actually working on that for currently. So yeah, so overall, our Earth AdaptNet did a quite a good job on all this, classifying these sections. So that's basically what I had to talk today. Before I leave the floor for questions, I think I just wanted to mention that deploying this model is what we are trying to do next. But also doing a quick Streamlit app, actually what we followed is gives you an idea of how how well the models are performing. So we did use time and again this app to see how basically, let me just refresh this. So here I'm showing few sections like how well is Deep Lab and Earth AdaptNet compared to each other? How well are they working on sections? So this gave us an idea of how to go about and do model improvement. So we did use this kind of technique in between when we were actually choosing the models too. So yeah, that's all I think I have for the presentation, and happy to take questions.
Awesome, Tanisha. This is great. So there was one question from Khalil. He's asking, did we use augmentation?
Yes, we did use augmentation in the data loader part. We did use augmentation. I think it was we did rotation, and then we did some kind of, I think it was a translation. I mean, the regular augmentations, but it's just not coming on. Like there were 4 or 5 types of augmentation that we actually used here to in the data loader part. Yeah.
Awesome. There is a question. I think it's a misplaced question, Sanjay, but I will still post it here. I think for my limited understanding of photometry, I think iphotometer has got to do with sun, right? So I did mention that in my comment. I mentioned that the drilling essentially models are now currently being explored even by NASA. And we are very actively looking at models to understand if in future or maybe even the near future there is application in drilling operations in other planets on other planets, and how would that look like. So it's currently in a review phase internally at our end. But I think iPhotometer, if you can elaborate on if that is what you meant, then obviously we can answer. But I think too, for my understanding, and I looked it up actually because I'm not an expert in that area, it just looks for measuring aerosols, right? That's what I thought it was. But again, if there is some other question, do please feel free to elaborate. I don't know. Tanish said, did you capture, is something else also in iphotometry and in
I'm actually
seismology?
not sure about
Yeah, okay.
iPhotometer. Yeah.
I was just looking at the questions, so I wanted to scan these. There's another question. Maybe Shashank has a question. How did you manage if the data was limited? And how did you avoid running into trap of inaccurate findings?
Yeah, so that's what I kind of mentioned. Like we that our data is was limited, so that's the reason we started out with patch models. So to get more data training, and one of the reason that we were also looking at is get an architecture which can train unlimited limited data set. So at every time we were looking at the matrices because we do have the original labels. So even for our test data set, we were measuring it with the test data set every time. So see that the accuracies are at par with them. So if any of those models were not doing well, when we did a test set, like when we run the matrices on the test, we got a total accuracy. Then we had accuracy for each and every sections. So that way we always were checking that the accuracies were at par, like not going anywhere. So this is how we kept a control of the inaccurate findings, basically. Yeah, this is the technique.
Cool. And there's another question, and I think that's the last question, and then we can close our chat. What was the size of the data set?
Data set, yeah. So the data set was how do I say? It's I don't know about the number what will come up, but it's 701 cross 400 cross 250. That's the volume we had. It's called the seismic volume. That's the basic volume we had, but I'm not sure what number it will be after you multiply all those three. Yeah.
Obviously. Awesome. So I guess we want to be very efficient this time. I know I saw the number of visitors are increasing as the session is going. That is a great way to measure that you were enjoying this session. Just like I said, we started a year ago. We went through a lot of ups and downs. We had some smart people coming in. Some people opted out, and that's the real way research is done. In a real world, research is not a rosy sort of laid path in which data sets is flowing in your direction and you're floating to NIPS and NeurIPS and celebrations are coming. In the real world, which is what the data which we are looking at, these are not celebrity images. These are not all these ImageNet data sets where it's easy to create an iteration and win your selection in NeurIPS. This is real world. So what I wanted to just add finally before we thank you all for joining this is, for us, it's super important to work in the industry. Applying AI into the industry is where research actually will eventually shine. And in a very strange twist of things, research should become the background, just like this beautiful green background I have. But research is supposed to hide into the background and shine on the field, shine inside your grocery store, shine inside your clinic. And this is what we're focusing on. Our collaboration with NVIDIA, and as many of you may not know, we are NVIDIA's Inception partners. In fact, that was one of NVIDIA's managers was just texting me that we have some free passes to get into conferences to share our stories. So we are working with industry leaders because we believe that moving beyond hype and excitement and into the real world where data is not organized, not normalized, and then eventually moving our product into pipelines and creating prototypes is what Tanisha just showed, is the only way you can succeed bringing your research to fruition. This is the most important thing, which is probably the most underrated thing on LinkedIn or on internet. But I think we want to stress that if you continue to be on that path, the opportunities for you to get yourself successful in your job, if you're a geologist, but also even apply these learnings into your own industry domain, which could be very different than specific drilling. You could be into, doing climate AI projects and trying to understand these models from a very different perspective. Your chances increase dramatically. So, moving from innovation to from invention to innovation and bringing your products from lab into production has worked very well for us. And I'm not preaching anybody here. The only way to make things happen is to bring these into production. This is what, for example, big and very successful entrepreneurs in this world, like Elon Musk, do on a daily basis. Learning and applying your learnings from one domain into another, and they come up with products and services. Now, we're a very small lab, but I'm extremely proud and so excited of my team that has been doing this, and they're becoming leaders. So in a way, I'm also kind of like research. I'll be disappearing into the background, and that's how actually great work is done. So awesome, Tanisha. Thank you so much for this.
Thank you, Terry.
I know you guys were not able to see Kwame, who actually worked so hard to make this happen. He presented in the GeoConvention conference. We will try to see in the coming weeks to release these models. And maybe at some point of time, we want to bring code implementation at some point of time in the future to make sure that people can try these. Right now, we are currently beta testing these models with a few enterprises, and we will also deploy this model inside one or two enterprises in the next very short time frame, to 3 to 6 months. So we are extremely excited. I mean, for us, for me, for Tanishta, for May, and for Foka, my co-founder, it is a dream come true, because you can only make innovation happen if you are putting into the hands of the real world, where people can actually come back with a million questions saying this is not working and fix it. And that is where we can measure our success. So we're very excited to have done this. And obviously, the underlying theme, which I don't want to talk too much about it, because we believe in doing rather than talking. In Deep Kappa, I'm the only male member in our management board. These ladies are the ones who are making this job. So, women are doing some awesome work in research, and they're doing some fantastic work in education. If you have your colleagues inside your company, these are people from these are women in your organization. They are excited to be part of you. Please embrace them, because this wouldn't have been successful if Ji Mei and Tanishta didn't drive this. It would have been impossible. So get good, diverse set of skills and beautiful minds together, and I think you'll have the same pleasure, like a fatherly pleasure that I have today, to look at these young people succeed inside your company with your colleagues. And I think that the questions around diversity, everything just vanishes because you're doing some awesome stuff together. So thanks, Tanishta. And thank you, everybody. We are excited to also bring some really awesome research. Make sure you look on our deepkappa.ai page. On our research, we'll be actually now publishing a lot of new research in neural network chip design. We'll be publishing paper. This paper already is out there. We'll be publishing it very soon. You'll have the link available. I published together with my colleague, with my good friend in Germany, a guide for authors and reviewers in dental. Just yesterday, we published on Elsevier. So we're coming up with a lot of research with our intention of bringing it to the market. And if you believe in this mission, do participate with us, because we want to make change. So we are serious about it, and we want to really work hard on it. So if you really believe in this, join the revolution. Thanks, everybody, and God bless. Take care and stay safe. Bye-bye. Bye-bye. Let me just share the last Khalil, thank you so much.
Thank you.
Yes, it is all thanks to you guys. Wonderful questions, and we'll see you guys soon. Take care. Bye-bye.